Hi, welcome to the second event of Meet the Magicians. I'm Alicia López Oramas. I'm a postdoctoral researcher at Instituto de Astrofísica de Canarias, and today I will be guiding you through this event. So, as you know, we will be talking about our latest magic paper on the detection of Geminga pulsar. And because of that, I have two of the corresponding authors of this paper with me. So first of all, let me introduce to you to Marcos López, who is a professor. Hi, Marcos. So you are a professor at Universidad Complutense de Madrid, right?
Yeah, correct.
Yeah, and you are the leading author of this paper. So thank you for being with us today.
It's my pleasure.
So we also have today with us Giovanni Cerivella. Hi, Giovanni.
Hello.
So Giovanni is a PhD student at the Max Planck Institute in Munich.
Yes.
And well, Geminga is the main thing you have been studying in your thesis, right?
Exactly. Yes.
Yeah, great. So thank you both for being here today. And since we are talking about galactic physics, we have today with us Daniela Hadash, which is an assistant professor at the Institute of Cosmic Ray Research. Hi, Daniela. We cannot hear you. Let me unmute you. Hi, Daniela.
Hello, everybody.
Yeah, so well, Daniela, as I said, is a convener, or let's say coordinator of the galactic group in MAGIC. As you know, in MAGIC, we have different groups, one for galactic physics, one for extragalactic physics, for dark matter and fundamental physics. And she is one of the coordinators of this galactic group. So just as a reminder for all of you that are at home, we have a live chat in YouTube, so you can ask your questions there, and at the end of the session we will come back to you. So as I said, the paper, if you want to have a look to it, can be accessed via Astronomy and Astrophysics, and the links are in our social media. So before going into the details of the paper, let's talk a little bit about MAGIC. So MAGIC stands for Major Atmospheric Gamma Ray. Major Atmospheric Gamma Ray Imaging Cherenkov Telescopes. MAGIC are two Cherenkov telescopes which are located in the Canary Islands, in La Palma Island exactly. So these two telescopes, they observe the most energetic universe. MAGIC observe what we call very high energy gamma rays, and they do it indirectly by looking at the products of this interaction between the gamma ray and the atmosphere, because the atmosphere protects us from the radiation we get from the outside. So when the gamma ray interacts with the atmosphere, it creates a cascade of particles. And these particles are traveling faster than light in the atmosphere. And then the so-called Cherenkov light is produced. This light these are flashes very fast, which last only a few nanoseconds, and they are like kind of bluish ultraviolet. So what we do with MAGIC is to detect this Cherenkov light, which tell us how this primary gamma ray arrived to Earth and where it came from, and it gives us some information about the astrophysical object in which it was generated. So just as a short reminder, gamma rays are the most energetic part of the electromagnetic spectrum. So with our eyes, we see only a small fraction of the light. We see basically the colors which go from the violet, blue, until the red. But this is just a tiny fraction of this electromagnetic spectrum. The gamma rays are in the most energetic part. So, for example, the gamma rays that are detected with MAGIC have between 100 billion and few trillion times the energy of the light that we see with our own eyes. So this is why we say that with MAGIC, we always observe the most extreme and violent universe. So in this paper, you will see also that we say that we have some observations done with a telescope called Fermi. So Daniela, you are part of the Fermi collaboration. Can you tell us a little bit what Fermi is and why we are sometimes interested in including observations with Fermi in our MAGIC papers?
Yes, sure. So, as you said, the MAGIC telescopes are on the ground. Fermi is a satellite that was launched by NASA in 2008. So it is orbiting our Earth and scanning the whole sky within 3 hours. So within 3 hours, we see once the whole universe, let's say. And the different thing about Fermi is that we can detect the gamma rays directly. The detector is quite small. It is about 1 square meter. And if a gamma ray comes and hits the detector, we can detect this gamma ray and reconstruct the energy and the direction where it comes from. It is very interesting for MAGIC to combine observations with Fermi, since the information we get goes also to another energy range. So MAGIC is sensitive from several GeV to some TeV energies, and Fermi is sensitive to an energy range a little bit lower, so from MeV to GeV. If we combine Fermi observations and MAGIC observations, we get much more information about the behavior of a certain source.
Okay, thank you for this nice explanation. And I have another question for you, Daniela. Before talking about the Geminga pulsar, can you let us know what a pulsar is?
Sure. So a pulsar, imagine you have a massive star, which has more mass than more than 10 times than our sun. And during its lifetime, it gets energy through fusion. So it is burning hydrogen, it is burning helium. And at some point, all these elements are burned. And the star is, let's say, dying.
Sorry, Daniela, can you unmute yourself?
I'm sorry. Okay. Yeah, so imagine you have a massive star, so 10 times more mass than our sun. And during its lifetime, it gets its energy by fusion, hydrogen. So it is burning hydrogen, helium. And once all these elements are burned, the core is collapsing. And through a supernova explosion, the outer parts are expanding into the universe, as you saw it now in the video. So the outer shells are emitted into the universe. And you saw these filaments in this video. This is material that got shocked in the interstellar medium, let's say. Okay. So, and what remains is a very massive star, a neutron star, which is, well, it can die into a neutron star, which is rotating very fast. This is a so-called pulsar. Yeah, you see here, the blue lines represent the magnetic field lines. It is rotating very fast. It can be seconds, it can be milliseconds. And we can detect emission from this object when the beam, for example, here, this violet beam is looking to the Earth. So imagine you have a lighthouse. You only detect the light of the lighthouse once the beam is really passing through your field of view. The same happens to a pulsar. So a pulsar is kind of a dead star, rotating very fast and has quite strong magnetic fields.
Okay, well, thank you. And now that we know what a pulsar is, let's go into the details of this paper, which is called Detection of the Geminga Pulsar with MAGIC Hints at a Power Law Tail Emission Beyond 15 gigaelectronvolts. So, Marcos, can you tell us a little bit more about Geminga and why this discovery is so relevant?
Okay, sure. Thanks, Alicia. First of all, let's talk a bit about the name of Geminga. Geminga is an Italian word that means there is nothing there. So this is quite striking. When people discovered this pulsar, they discovered it to emitting gamma rays. And it was quite strange for that time because most of the pulsars that were discovered were emitting radiation in radio or X-rays. But it was the first pulsar, one of the first pulsars in which the radio emission was detected at the same time. And it was quite interesting. Second thing is that this pulsar is relatively old. This pulsar was born after the explosion of a star that occurred 300 years ago, so quite old. Also, this pulsar is very close to us, so it was quite interesting to study it. So what made this discovery quite interesting is that back in 2008, we discovered with MAGIC the first pulsar emitting radiation up to very high energies. And the question that arose there was that we wanted to know if this pulsar that we discovered in 2008 was the only pulsar emitting at very high energies or not. Actually, this opened a whole new branch of research in this field with pulsars. And we have been trying for years, basically more than 10 years, to try to figure out if this pulsar, this Geminga one, was also showing peculiar behavior. I mean, a behavior that, meaning that this pulsar is able to emit also gamma rays up to very high energies. So after many trials, we saw that this pulsar was able to emit gamma ray radiation up to energies never seen before in this object. So this is the second pulsar ever discovered in the northern hemisphere, which is exhibiting this behavior. And this is very important for modeling the physics behind the working of neutron stars.
And for example, you have said that this is a relatively old pulsar, no? And in the paper it's commented that this is the first middle-age pulsar that have been detected at to very high energy gamma rays. So, for example, Giovanni, can you tell us a little bit more why this is also important?
Yeah, sure. So essentially it is important because we know very few of these objects. As Marcos said, we know 2 of them in the northern sky and 1 in the southern one. So we are not really sure about how they evolve with time. So detecting a pulsar which is, say, in her 60s or 50s, yeah, it's a nice discovery because we did not know whether such old objects can still emit gamma rays like the youngest ones. Yeah.
And Giovanni, I think you have created a kind of device to show us how a pulsar works. Do you have it there?
Oh, yeah, right. So I will try and make a small experiment. Yeah. So be careful. And I've made this small pulsar, pulsar like it's just a ball. It's similar to a pulsar because it's made of steel, which is a conductive material, and also pulsars are very conductive. But unlike the true pulsars, this ball has no magnetic field. So I've just attached a couple of magnets here to simulate the magnetic field of a pulsar. Yeah, and now I will try to make a reverse pulsar. Experiment live. You only get this with experimental physicists. Yeah, and I have a tension generator, a voltage generator, and now I will try and see if we can make this pulsar spin. Yeah.
It was also as fast as in real life.
Okay, probably I should stop doing this because it's getting sparks and smoke everywhere. I don't want to set on fire my house.
Yes, please. So go ahead.
This is practically a reversed pulsar. So in this experiment, we have put some voltage to the magnets, and the pulsar started spinning. In reality, what happens is that the pulsar is already spinning. It's spinning very fast, in fact. And this, together with the magnetic field, produces a current. And just as you saw sparks coming out of the magnets, more or less, we get gamma rays and other types of radiation out of the pulsar.
Wow. Thank you for this nice explanation. And since we are talking about pulsars, now we know that we have detected Geminga. Marcos also talked before about another pulsar that we discovered in MAGIC a few years ago, CAP. So how many pulsars have been detected in very high energy gamma rays? Can you tell us, maybe Marcos, Giovanni?
Yeah, we know for sure 3. 2 in the northern hemisphere, another one in the second hemisphere that is called Vela, and there is also almost detected in the southern hemisphere, but I mean, the publication is still to be published. So let's say between 3 and 4 we know today.
Exactly. So we have these 3 pulsars, and I think we should see a few videos about them. So please, if you're at home and you're using headphones or something, lower a bit the volume, because this might get a bit, the sound might get a bit annoying, okay? So let's, we will see some videos, and I want you to tell me, guys, what is that we are listening and why they sound so differently. So first, let's go and see the video. So first we can go, okay, Geminga pulsar. So now we can go with the Vela pulsar. As you can see, it sounds very differently. Okay, and now, please lower your volumes. Okay, I think it's fine. Okay, so can any of you maybe tell me why they sound so differently? Maybe Giovanni?
Yeah, right. So basically the frequency, the pulsation that you could hear is just the rotational period of the pulsar. So Geminga is an older pulsar, and so it is spinning a bit slower, and therefore the beat was also slower. Vela is kind of a young one, but it still say an adult pulsar, yeah. So you could hear it spinning a bit faster. And Crab is a very young one. It was born less than 1,000 years ago. So for an astronomical object, it's practically a newborn star. So you could hear it spinning very fast, yeah.
Yeah, so basically what we were listening was exactly what you say, no? The rotation of the pulsars.
Exactly, yeah.
So, and now I want to ask you about a little bit more technical question, because so I was in the beginning, I was saying that with magic normally we detect light which is like 100 billion times more energetic of the light that we see with our own eyes. So this is what we would say in the 100 giga electron volt domain, no? So, but in the paper you detect emission from as low as 15 giga electron volts, and you talked about some trigger. So can you tell us a little bit about the challenges of detecting at such a low energies?
Yeah, well, so yeah, pulsars in the group of objects that emit gamma rays and that we observe with magic, pulsars are kind of the ones that emit at lowest energies, yeah? So we say below 100 GeV. There are some exceptions, but it's more or less for magic what we regard as low energy.
So
and
let's say that Fermi would detect more normally detects more pulsars than magic?
It detects many more pulsars. So there are roughly 270 pulsars detected with Fermi, and with Cherenkov telescopes such as magic, we only see 3. So it's a factor 100, say, difference.
Okay.
And the difficulty is because these gamma rays that penetrate in the atmosphere and that produce the Cherenkov radiation that we observe with the telescopes, since they have a lower energy, they produce less light, and so it's more difficult to see these gamma rays. So the magic telescopes were able to detect the Geminga pulsar because in the past years, we worked very much to improve the telescopes and its detection system with this machine that we call the sum trigger. Here you can see a gamma ray that enters in the atmosphere, yeah, and produces a shower of particles. And this shower of particles produces some Cherenkov radiation, yeah. This was what Alicia was explaining at the beginning. And then these reach the magic telescopes, but we somehow have to be able to tell whether we see such an event or whether it is just some noise from the background, yeah? And this machine that is doing this job is the trigger, and the sum trigger, which is the machine that we have used in MAGIC to do this, is a machine that was especially designed to be able to grasp really the dimmest signals from the skies.
Yeah.
Great. So basically, Marcos, can you want to say something else about the sum trigger?
Yes, maybe to put this field into context, I mean the field of trying to see pulsars in gamma rays. I think we have to remind the audience that we have two different techniques to detect gamma rays. We can either put a telescope in orbit in a satellite, or we can put a telescope, a gamma ray telescope on Earth. But the problem is that the space telescope can detect gamma ray radiation as to certain energies, typically, let's say, 10 GeV, which is 10 billion times the energy of the light, of the visible light. And from ground, we can detect sources, gamma ray sources, but at higher energies. And the important thing with pulsar is that it was predicted, I mean, due to different theoretical models, that the most important thing, or the most important region to study this object in gamma rays was just the energy window that was between the space telescope and the gamma ray telescope. So space telescopes were not able to answer what was going on the gamma ray emission of pulsar because they were not big enough to detect the emission of these energies. And on the contrary, ground-based gamma ray telescopes that are very large and very big couldn't either to detect that, the emission from pulsar, because I mean the emission from pulsar goes just in the, let's call it like this, forbidden region for gamma ray astronomy. So many groups in the world, either people working with a space telescope or people working with ground-based telescope, have been trying very, very hard during the last 20, 30 years to develop new techniques, new instruments, as we did with MAGIC, as just Giovanni explained, in order to catch this faint emission from pulsars. Not only to detect them, but only to measure the characteristics of this emission in this energy region in order to disentangle between different emission models. So for that, this kind of detection, like Geminga one with MAGIC, is quite important for the theoretician because it can help us to understand the physics behind this emission.
Yeah, so basically this detection also, I mean, it's not something that was, we were not just lucky. We also developed some system to really go as low in energy and detect this pulsar, right? So this, I mean, this is an effort that has been going on for years to develop this system, make it work, and detecting the pulsation. So such a great result, right? I guess you are so happy about it.
Actually, this new technology that we developed for MAGIC is going to be used also for the next generation of Cherenkov telescope that is called CTA, the CTA Observatory, that is going to be placed on the Canary Island, also on the southern hemisphere in Chile, is going to use this technology that we have developed for MAGIC. So we are happy also for that.
Great. Actually, the video that we put, the latest video we put where we saw this Cherenkov cascade and how it looked in the camera was taken from Cherenkov telescope array. So let's go for a last question before going to the live chat. So can you tell us a little bit more about how these gamma rays are generated in the pulsar, maybe about the different models that can explain in a few words, and very easy, maybe Marcos or Giovanni?
Okay, in a few words, I will try to explain it. So, I mean, the physics around pulsars is quite interesting. It's very nice. What happens in first place is that, I mean, you have a very, very intense magnet that is rotating very fast. As we studied in the school, when you have a magnetic field that is rotating, this magnetic field induces an electric field. In this case, the induced electric field is so high, so intense, that it is able to pull out particles from the stellar surface. These particles are going to be accelerated up to very high energies around the star. And as you know, when we have particles accelerated, they radiate energy. And they radiate a very high energy in this case. So basically, people trying to model what is going on in pulsars and develop two different kind of models. In one model, the thing that the emission is coming very close to the neutron star surface, and the other model, in the competitive model, people think that the emission is coming farther away from the neutron star. So, as I said before, in order to see or in order to understand which is the real model, the good model, we have to measure the emission in this narrow window that lies between the Space Telescope and ground-based gamma-ray telescope. But also there are different physics involved. For instance, there is one mechanism which is called curvature radiation that is very similar to synchrotron radiation, which is maybe familiar to the audience. Another mechanism is inverse quantum. Maybe Giovanni can explain a little bit more on these two different mechanisms. Curvature radiation versus inverse quantum.
Yeah, so I'm waiting to, so essentially the space around the pulsar is filled with this magnetic field, and it is also filled with particles. And the particles kind of surf on the magnetic field lines, but by doing so, they are forced to orbit in a curved path, and like this, they experience some force and they radiate photons. So this is what we call curvature radiation. Instead, the other mechanism, the inverse Compton one, you can imagine it's like I had the ball here just before I had the ball. You can imagine this is my photon, my gamma ray.
Giovanni, we need to go for questions. So
I go very fast. So you get this gamma ray, which say it has a lower energy. It is going quietly on its road, and then say a very high energy particle, an electron comes and hits it, and then this goes away very, very fast and with a higher energy. And this is the inverse Compton procedure. So what we have seen is that probably this emission that we see with magic is caused by this inverse Compton, which we were not sure before whether it could happen around Geminga.
Yeah.
Great. So, I think it's now time for questions, now that we know a little bit more about the modeling and so please, people, don't be shy. You can ask in our live chat. So in the meanwhile, while people gets a little bit more less shy, we have an offline question. So let's go first with this offline question, which I think is for Daniela, let's say, okay? Because somebody is asking, are pulsars always alone in the universe, or can they be found somewhere else? No, I cannot hear you.
Yeah. Well, actually, most of the massive stars that we know, they are living in so-called binary systems. So we have two stars orbiting each other. And as I told before, these massive stars, when they die, they can leave a pulsar behind. So these two stars are orbiting each other. One of them dies in a supernova explosion, and what remains is this spinning neutron star, this pulsar. And still, the massive star and the pulsar, or whatever star and the pulsar, are still orbiting each other. So the pulsar, like you see in this nice movie, the pulsar is this pink dot orbiting a massive star. And in these so-called binary systems, we find quite a lot of pulsars. And in this system, what can also happen, that the pulsar gain spin energy. So they get material, they are, let's say, accreting, sucking material from the star, getting accelerated, and they can spin up to milliseconds. So this, millisecond is much, much faster than a second. So in 1 millisecond, it spins once. So you can imagine that these guys are rotating quite fast. So pulsars don't have to be alone. They are very often bound.
Thank you so much, Daniela. And we have a live question by Marina. In which constellation is Geminga?
So maybe I can answer. Geminga is in the Gemini constellation, so in the twins. And this was also part of the play of words for why it was named like this. As you've heard at the beginning, Marcos explained Geminga, it's a dialect of Italian from Milano that actually means it's not there, because they were looking for it and they didn't see anything. But the name was also chosen because it has this, it kind of reminds the name of the constellation, Gemini.
And also we have another question by Bruno, who lives in Cork, Ireland. He's one of our youngest followers, and well, he's.
What is the pattern on the ball?
What is the pattern of the ball on the ball?
I mean, on the ball in the video.
You see
okay.
that.
This one, yeah, okay. So actually, the pattern on the ball, it's a draw. That's a drawing that I made. So it's kind of a fantasy, because nobody really knows how a neutron star looks like, and there's nobody on Earth that knows that. But actually, these kind of fluorescent lines that I draw there, they have some meaning, because you remember Marcos was saying that these pulsars are very electric, yeah, and that somehow they produces a lot of particles. So in some models, these particles are created like in a lightning. So you can imagine it's like one of those nice balls that you touch, and then you have all the sparks and lightnings that come close to your hand, and it's a bit like this. So that's why I've put these nice alien-looking fluorescent pattern on the pulsar.
Okay, so I think there are no more live questions, and we have already been here for half an hour. So I just want to thank all of our invited guests. So thank you, Marcos, Giovanni, Daniela. Thank you for joining us, and thank you.
Maybe if the people have more questions, they can put them in the comment.
Yeah, exactly. You can put it in the comments. You can also write to us in our social media, Facebook, Twitter, and Instagram, and we will answer to you there if you are curious. Look, we have a question in Facebook. Hi, this is a bit basic, but why pulsars rotate slower when older? The speed of rotation depends of the star which the pulsar comes from. Can we detect different particles depending on the pulsar stage? Well, thank you, Silverin.
Well, these are really a lot of questions, and they are all very good.
Good, yes.
So,
okay, actually, all pulsars rotate faster than younger ones. Typically, because we find all pulsars in binary systems, as Daniela explained it before. So when you have this binary system, we have the pulsar and a massive star. And the pulsar is starting to accrete material from the nearby star. And when this pulsar is accreting the material, the rotation rate increases. So actually, older pulsars typically are faster than younger ones. Because of that, we call this the second pulsars.
Yeah. So this is the very old pulsars. They may go much faster, because of this. So they accrete material on the star, and so they spin up. But for the pulsars that we are studying, they actually go slower because the energy that produces the radiation that we observe comes from the rotation of the pulsar. So the more they radiate energy, and the more they lose rotational energy, so they go slower. And this is why the older pulsars, they in the class that we are speaking about, they are called the rotational pulsars. They they spin down. And then there were another couple of questions, I think, from the same person.
I was trying to check. I cannot remember. I don't know if...
Yeah, they were asking if we can detect different particles depending on the pulsar.
Very good.
This is very good question. So actually, Geminga, the pulsar that we studied, it's a very close pulsar to the Earth. It's kind of 600 or 800 light years. For an astronomical object, it's really close. So actually, there are some hypotheses that some particles that come from the pulsar reach the Earth, and that we can measure them here. But this is something very, very speculative. To say something about the type of particles that emit the radiation that we observe, I think that we will have to wait to have some more pulsars. Yeah, now we have 3. Maybe when we will see a bit more, probably we will be able to say what types of particles emit this radiation in each of the pulsars.
Now, one of these are antimatter, are positrons. So pulsars are antimatter emitters. For instance, Geminga is one of the stars that are supposed to emit a lot of positrons. This
Exactly, yes. So I saw that there was a question whether pulsars will be observed also with the CTA. Marcos, I guess maybe you can answer best to this one, yeah?
Yes. Actually, I mean, we want to discover new pulsars with the CTA, but also we want to observe the pulsar that we already know, for instance, Graf and Geminga in the northern sky, in order to have a better reconstruction of the mission. So now we have that, for instance, with MAGIC, we have detected in this paper Geminga, but we would like to make further observations in order to know with more detail the details of the mission. So the story is not over. I mean, this is just the beginning, for instance, with Geminga. So we want to continue understanding how these pulsars are working.
Great. So do we have any more questions? I don't see if we have.
Otherwise, you can just poke us on Facebook, Instagram, Twitter, and whatever you want. Yeah.
Yeah, so I think there are no more live questions, as Giovanni says. You can also write to us in the social media. So thanks again to all the authors, to Daniela. Thank you to Marina, which is in the backstage. I think you can come live if you want to say hello. So Marina, which has been helping us in the backstage. And well, thank you. Yeah, and thank you to all of you at home. And well, see you in the next Meet the Magicians. Okay, so bye.
Ciao.
Bye.
Bye-bye.